Welcome students. In our previous class, we came across three types of adsorption isotherm, that is Freundlich, Lachmuir and bed adsorption isotherm. We saw what is Freundlich and Lachmuir adsorption isotherm. In this class, we are going to study about bed adsorption. Before going detailed into derivation of bed equation and bed adsorption isotherm, we shall discuss on 5 different types of isotherm. First, we will see type 1 adsorption isotherm. As you can see in the figure, type 1 is the simplest isotherm. It corresponds to unimolecular adsorption. And this graph can be easily explained using Lachmuir adsorption isotherm. And it is characterized by maximal limit in the amount adsorbed. Examples of type 1 adsorptions are adsorption of nitrogen or hydrogen on charcoal. Next is type 2 adsorption isotherm. Type 2 adsorption isotherm shows large deviation from Lachmuir model of adsorption. The intermediate flat region in the isotherm corresponds to monolayer formation. Example of type 2 adsorption are nitrogen adsorbed on iron catalyst and nitrogen adsorbed on silica gel. Next is type 3 adsorption isotherm. Type 3 adsorption isotherm also shows large deviation from Lachmuir model. This isotherm explains the formation of multi-layer. There is no flattish portion in the curve which indicate that monolayer formation is missing in this adsorption isotherm. Example of type 3 adsorption isotherm are adsorption of bromine at 790 degrees Celsius on silica gel or adsorption of iodine at 790 degrees Celsius on silica gel. Next is type 4 adsorption isotherm. In type 4 adsorption isotherm, at lower pressure, region of graph is quite similar to type 2. This explains formation of monolayer followed by multilayer. The intermediate flat region in the isotherm corresponds to monolayer formation. The saturation level reaches at a pressure below the saturation vapor pressure. This can be explained on the basis of possibility of gases getting condensed in the tiny capillary pores of adsorbent at a pressure below the saturation pressure of the gas. Example of type 4 adsorption isotherm are adsorption of benzene on iron oxide at 500 degrees Celsius and adsorption of benzene on silica gel at 500 degrees Celsius. Next is type 5 adsorption isotherm. Explanation of type 5 graph is similar to type 4. Example of type 5 adsorption isotherm is adsorption of water at 1000 degrees Celsius on charcoal. Type 4 and type 5 shows phenomenon of capillary condensation of gases. Now, we shall move on to the mathematical derivation of bed equation and corresponding isotherm. The name bed is derived from the names of 3 scientists, Stephen Werner, Paul Emmett and Edward Teller, that is B from Werner, E from Emmett and T from Teller. Bed theory explains the physical adsorption of gas molecules on a solid surface, and this theory applies to system of multi-layer adsorption. It is used as an important analysis technique for the measurement of the specific surface area of materials. The basic assumptions that are made in this theory are, first one is the gas molecules undergo multi-layer adsorption on solid surface. Next is the principle of Lachmuir theory can be applied to each layer. A dynamic equilibrium exists between successive layers. At equilibrium, the rate of evaporation from a particular layer is equal to the rate of condensation of the preceding layer. The enthalpy of adsorption of the first layer, that is E1, is a constant, whereas that of any layer above the first layer is the energy of liquefaction of the adsorbate. It represents EL. Next assumption is that condensation forces are the principal forces of attraction. Now, we are going to see what is Bett equation. It is given as P by V into P0 minus P, that is equal to 1 by CVm plus C minus 1 divided by CVm into P by P0. V is the volume of gas adsorbed at a pressure P. Vm is the volume adsorbed when surface is covered with a monolayer. C is a constant and its value can be calculated from the equation, that is C is equal to e to the power E1 minus EL divided by RT. E1 is the energy of adsorption of first layer and EL is the energy of liquefaction of the adsorbate. Let us see how they have derived this equation. The diagrammatic representation of multi-layer adsorption is shown here. In this figure, S0 represents number of vacant sites. S1 is the number of sites at which unimolecular layer has occurred. S2 is the number of sites at which bimolecular layer has occurred. Thus, Si denote the number of sites at which ith molecular layer has occurred. Now, consider first layer. Rate of adsorption on the bare surface, that is equal to A1 P S0. Here A1 is the adsorption rate constant of first layer, P is the pressure, S0 is the vacant site. Rate of desorption from the first layer, that is equal to B1 into S1 into e to the power minus E1 by RT. B1 is the desorption rate constant, S1 is unimolecular layer, E1 is energy of adsorption of first layer and it is assumed to be constant. At equilibrium, rate of adsorption, that is equal to rate of desorption, that is A1 P S0, that is equal to B1 into S1 into e to the power minus E1 by RT. From this equation, we can find out the value of S1, that is S1 is equal to A1 divided by B1 into P into e to the power E1 by RT into S0. We can substitute A1 by B1 into P e to the power E1 by RT, that is equal to Y. Then S1 becomes equal to Y S0. Next, consider the second layer. In the second layer, rate of adsorption is A2 P S1. Rate of desorption is B2 into S2 into e to the power minus E2 by RT. At equilibrium, rate of adsorption equal to rate of desorption, that is A2 P S1, that is equal to B2 into S2 into e to the power minus E2 by RT. Similarly, for the third layer, the equation at equilibrium is A3 P S2, that is equal to B3 into S3 into e to the power minus E3 by RT. Here A3 and B3 are adsorption and desorption rate constants. Thus, for the ith layer, the equation at equilibrium becomes AI P Si minus 1, that is equal to Bi into Si into e to the power minus Ei by RT. Now, let us consider the equation for S2. S2 is equal to A2 by B2 into P into e to the power E2 by RT into S1. We have already seen that E1, which is the energy of the adsorption of first layer, and it is assumed to be constant, and the energy of subsequent layer is assumed to be the energy of liquefaction of gases and is denoted as EL. That is, E2 is equal to E3, that is equal to E4, etc. up to EI, that is equal to EL. Similarly, the fraction of rate constant for subsequent layers are equal, and it is denoted as B2 by A2 is equal to B3 by A3, that is equal to B4 by A4, etc. up to BI by AI, that is equal to G. So, the equation for S2 becomes equal to P by G into e to the power EL by RT into S1. Substituting P by G into e to the power EL by RT, that is equal to X. Then S2 becomes equal to X into S1. Substituting the value of S1, that is YS0 in the equation for S2. Then S2 is equal to XYS0. If S2 is equal to XS1, what is S3? S3 is equal to X into S2. Substitute the value of S2, that is XYS0 in this equation. S3 becomes equal to X square YS0. Similarly, S4 is equal to X raised to 3 into YS0. So, Si can be written as, that is Si, that is equal to X to the power I minus 1 into YS0. Multiplying and dividing by X on both sides, that is Si into X by X, that is equal to X to the power I minus 1 into XYS0 divided by X, we get X to the power I into X to the power minus 1 into X to the power 1 YS0 divided by X. X to the power minus 1 and X to the power 1 cancels off. Then we get X raised to I YS0 divided by X. Substitute Y by X as C in the above equation. Then Si becomes equal to X to the power I into C into S0. Next, we can see significance of C. It is a part of this derivation. C is equal to Y by X. Y equal to A1 by B1 into P into e to the power E1 by RT. X is equal to P by G into e to the power EL by RT. Substitute this X and Y in the equation of C, then we get C is equal to A1 by B1 into P into e to the power E1 by RT divided by P by G into e to the power EL by RT. By rearranging, we get A1 by B1 into G into e to the power E1 minus EL by RT. Then, if we know the magnitude of C, we can find the nature of adsorption. The first case, when E1 is very much greater than EL, the value of C becomes very large. The BET equation reduces to Lachmuir isotherm for monolayer adsorption. In the next case, that is when E1 is greater than EL, an intermediate value of C is obtained. This gives type 2 adsorption isotherm, indicating multi-layer adsorption. And next is when E1 less than EL, small values of C are obtained. This result in type 3 adsorption isotherm, where multi-layer adsorption begins even before the completion of monolayer adsorption. Now, let us continue our derivation of BET equation. Total surface area of the adsorbent A is equal to sigma I equal to 0 to infinity Si. Total volume of the adsorbed gas, that is V, equal to V0 into sigma I equal to 0 to infinity ISI. Here V0 is the volume of the gas adsorbed on 1 centimeter square of the adsorbent surface monolayer coverage. Now considering V by A, we can write it as V by A, that is equal to V0 into sigma I equal to 0 to infinity ISI divided by sigma I equal to 0 to infinity Si. Rearranging this equation, we get V by A V0, that is equal to sigma I equal to 0 to infinity ISI divided by sigma I equal to 0 to infinity Si. We can substitute A V0, that is equal to Vm. Vm is the volume of the gas for monolayer coverage. Then V by Vm, that is equal to sigma I equal to 0 to infinity ISI divided by sigma I equal to 0 to infinity Si. In the next step, we are splitting the summation term of both numerator and denominator, such that sigma I equal to 0 to infinity changes to sigma I equal to 1 to infinity, added with the initial term. So, now the equation becomes 0 plus sigma I equal to 1 to infinity ISI the whole divided by S0 plus sigma I equal to 1 to infinity Si. Then we take common term CS0 outside the summation term, so that we can cancel off common term from both the numerator and the denominator. Once again rearranging, we can write equation as V by Vm, that is equal to CS0 into sigma I equal to 1 to infinity I into x to the power I the whole divided by S0 into 1 plus C into sigma I equal to 1 to infinity x to the power I. Cancelling S0, we get V by Vm, that is equal to C into sigma I equal to 1 to infinity I into x to the power I the whole divided by 1 plus C into sigma I equal to 1 to infinity x to the power I. We know that the value of this summation are such that sigma I equal to 1 to infinity I into x to the power I, that is equal to x by 1 minus x the whole square, and the value of sigma I equal to 1 to infinity x to the power I, that is equal to x by 1 minus x. So that we substitute these values of summation to our equation, and the whole equation we get as V by Vm, that is equal to C into x by 1 minus x square the whole divided by 1 plus C into x by 1 minus x. Rearranging this equation, we get Cx by 1 minus x the whole divided by 1 plus C minus 1 into x. Taking 1 minus x to the denominator, we get V by Vm, that is equal to Cx divided by 1 minus x into 1 plus C minus 1 into x. One form of BET equation is what we have derived now, that is V by Vm, that is equal to Cx by 1 minus x into 1 plus C minus 1 into x. By simple rearrangement, this form can be written as x by 1 minus x into V, that is equal to 1 by CVm plus C minus 1 divided by CVm into x. Substituting x, that is equal to P by P0. Here P is the equilibrium pressure of the gas over the surface. P0 is the saturated vapor pressure of the gas at experimental condition. Then wet equation becomes P by P0 minus P into V, that is equal to 1 by CVm plus C minus 1 divided by CVm into P by P0. We can relate this wet equation to equation of straight line, that is y equal to mx plus c. Here y, that is equal to P by V into P0 minus P, and x is equal to P by P0. So, if we plot a graph with P by V into P0 by P against P by P0, we get a straight line, and the slope of this straight line will be equal to C minus 1 divided by CVm. Extrapolating this plot to x is equal to 0, we get the intercept 1 by CVm. So, this is wet equation and wet isotherm. So, dear students, in today's class we have discussed 5 different types of adsorption isotherms: assumption of wet equation, derivation of wet equation, and wet isotherm. Thank you.